We'll start. I hope all of you can hear me, and so we will briefly recall what we did last time. So we saw what is a topological group, and so G is a topological group, and we saw that we saw a lot of things. In fact, we saw that the action, the translation action, which we denoted by TG, from G to G, is a homeomorphism. We saw the properties of that, and most importantly for us, later on we will see that if G mod H, regardless of whether H is a normal subgroup or not, we might require H to be a closed subgroup. G mod H is a homogeneous space under the action of G. We saw the definition of homogeneous space, everything last time, under G. So the idea is G mod H gets the quotient topology from G, and you have a left action for, so which we see as left translations, and under these translations G mod H becomes a homogeneous space, right? So today we shall see that in some cases, more than having a topology, we will have a measure on the group G. So it makes sense to integrate on those spaces. So as I said, the main idea or the main theme of our study is to study objects on this quotient space, and in order to do that, we need to properly use the action of G. So in most cases what happens is, whatever structure you have here on G, you will be able to push forward here. I mean, this is not true always, but this will happen in most of the cases, and it would be very nice to integrate in such a space. And in order to do that, following the principle that we were having for the last two lectures, we'll start. So we'll try to define a measure on G, and we'll see when we can push that measure forward to a measure on G mod H. So this was done by Haar. Haar is the name of a mathematician, and so before I give the result of today, let's recall a little bit of measure theory. So we all know what a measure is, and yeah, before I go forward, I need to define what is a locally compact group. So from now onwards, all my topological groups are assumed to be Hausdorff, and we shall not consider any other case. So all my groups are assumed to be Hausdorff. So what is a locally compact group? Which is a topological group which has a compact neighborhood, or which has which has a compact set X such that the interior of X, which is X naught, XO, is non-empty. So if G has a compact set with a non-empty interior, then we say that G is locally compact. So the terminology comes from a locally compact space, locally compact topological space, where it is enough to have a compact neighborhood around a point. So every point should have a compact neighborhood. That is basically the definition of a locally compact space. But because, as I said, you can translate sets, right? You can translate open sets, you can translate closed sets by these homeomorphisms. If I have one such set which is compact with a non-empty interior, then I can translate that set and get compact neighborhoods around every point. Is that okay? So this is equivalent to the topological definition. So let me repeat, the actual topological definition requires the topological space every point in the topological space to have a compact neighborhood, which means there exists what this means is you have for every x in x, okay, x is probably a bad notation, let's call T as our topological space, and for every T in T we have there exists what is the U contained in K. K is compact, U is open, and it should contain X. This is what we mean by a locally compact topological space. Now in the case of topological groups, as we saw earlier, we can translate these sets without changing their topological properties. So any translate of X will again be a compact set because translations are homeomorphisms, and the corresponding interior will again be non-empty, but it will be around a different point. Okay, so this is, if you are not convinced, you can try these things for yourself. Just have to play with the definition and the properties of the translation map. Okay, so this is a locally compact group. Now let's start with some recollection of some definition from measure theory. Recall measure theory. If if T is a topological space with a measure with the topology tau, or let's call it something else, with the topology, I don't know what is it, I know T is a topological space. I can't think of any symbol for the topology. So then we all know that there is a sigma algebra on T. The most standard sigma algebra on T is the Borel sigma algebra, which I am noting by B of T. Okay, we all know the definition of the Borel sigma algebra. Now, so suppose you have a measure mu on the Borel sigma algebra. So you have a measure, positive measure, we are not going to signed or complex measures. Mu is a measure on the Borel sigma algebra to R plus. Okay. Now we say that this is mu is a Borel measure if for every compact set. So K will denote compact sets now. U and V were denoting open sets, K will denote compact sets. Okay. So for every compact set K, and of course K is in the Borel sigma algebra because I have assumed a T is Hausdorff. That is a standard assumption that I am making. T is Hausdorff. So every compact set is a Borel set because the complement is open. That is something which you can show. And so for every compact set K, mu of K should be finite. Okay, I should put union infinity. Mu of K is finite. If this happens, then I call the measure a Borel measure. This is fairly standard definition. Now if furthermore I will call a measure as a radon measure, I will call the measure mu as a radon measure if the following happens. The first one is called outer regularity. Okay, what does it say? So for every E in the Borel sigma algebra, mu of E is equal to infimum over mu of U, where U is an open set as always and U contains E. This is the first condition. This is called outer regularity. This means you should be able to approximate the measure of E by taking from the outside. I mean, I hope you have seen this before and you know what all this means. So the second thing is inner regularity. What does inner regularity say? For every open set U, mu of U is equal to supremum of all the compact sets, all the measure of compact sets contained in U. Okay, so for open sets you should be able to approximate them from the inside, and for general Borel sets you should be able to approximate them from the outside. The first thing is in fact how you define the Lebesgue measure, outer measure. So in the case of R, your open sets can be written as a disjoint union of open intervals in R, and then this is precisely how you define the usual Lebesgue measure. Okay, now we have defined these things. So if furthermore G is, so all this was for a general topological space. Now we shall restrict ourselves to topological groups. So we have the last definition. If G is a topological group, which again I am assuming is Hausdorff, then you have a measure mu from the Borel sigma algebra of G to R plus naught union infinity. Okay, you have a measure on the space. Then we say that mu is a Haar measure. Mu is a Haar measure if mu is translation invariant. So we say that this is a left Haar measure, okay, if mu is left translation invariant. What does this mean? Because we have seen that translations are homeomorphisms, for every E in your Borel set, Borel sigma algebra, okay, the translate of E, left translate of E will also be in the Borel sigma algebra for every x in G. Because translations are homeomorphisms, they preserve open and closed sets, and these are invertible maps. These translations are invertible maps, so you can take them inside union, take them inside intersection, because they are invertible. Okay, this is, if you are not convinced, again this is a small exercise which you can try yourself. So the translate of any Borel set is again a Borel set. What I require is, I want mu of E to be equal to mu of xc for every E in BG and x in G. Okay, so the Haar measure is a, so this has to be a radon measure. Yes, we defined radon measure.
You have just given this only
Huh.
outer regularity and inner.
Is this okay? A radon measure is a measure which satisfies these two properties. Okay, I thought that was clear. So first of all, it has to be a Borel measure. It should be defined on the Borel sigma algebra, and the measure of every compact set should be finite. And on top of that, these two conditions should be satisfied. It should be outer and inner regular. And if you want it to be a Haar measure, you should have a group acting on your space, and I mean your G itself should be a topological group, and you want it to be translation invariant. So since we have started from the first lecture itself, I said that we are not assuming any sort of abelian condition on G. G can be non-abelian, and we will stick to the left action. Whatever we are doing, it is in the left side. So that is why we will consider the left Haar measure. If you had started with the right action, you would be able to get a right Haar measure. So let me just mention it here. Similarly, right. Okay. Similarly, we can have a right Haar measure. Now we shall get to this in a bit. Although the theory is same in the both left and right case, the actual Haar measure that you get might not be same. So that might be different. We will see examples of such cases, and okay, most probably not today. We will see them tomorrow. Anyway, right. So now we state the main result theorem. Due to Haar, okay, every locally compact group has a Haar measure or admits Haar measure. Okay, so if you have a locally compact group, then it is guaranteed that you have a Haar measure, and this is both left and right, admits a left and right. Okay, so this is, you must appreciate the strength of this theorem. It is not just giving us any measure, it is a measure which is finite on compact sets first of all, which is inner and outer regular measure, and then it is translation invariant. Okay, so without knowing these properties, we have been using these things when we were doing basic integration back in high school, right? We were just, so let us take a small example. If you wanted to integrate, let's say 0 to 1 f of x dx, okay, we will make the change of variable t is equal to x plus 1, and we will just simply write dt is equal to dx, right? So what does this mean? Okay, this is precisely the translation invariance that we are talking about, because the set of real numbers is a topological group, as we saw, and there all translation literally means adding and subtracting elements. Literally you are translating x to x plus 1, right? And dt, which denotes the measure, is unchanged. If you don't understand how dt denotes the measure, you can think of dx as a small length, small arbitrary small length in the real line. So if this is your real line, then dx is so this is, let's say, 0, this is, let's say, 1, this is, let's say, 2. Okay, you take a small length here. Okay, say that this is dx, and if I translate this here, x going to x plus 1 or t is equal to x plus 1, then the same length, the measure will not change. The measure of this small interval is the same as the measure of this small interval. That is what it means for a measure to be translation invariant. Okay, so again, this is a very, very strong result, and this is in the core of Fourier series or Fourier theory, and how you can do a similar notion of Fourier analysis on locally compact groups. Without this you cannot do it. Without this you can't most probably study differential equations on let's say some compact symmetric space, for example. So what this allows us to do is that we have a lot of we can integrate on these spaces now. So that will allow you to study study L2 spaces, LP spaces. Now it makes sense to talk about L2 of G. It makes sense to talk about this now, because you know how to integrate on G, right? Because if you don't have a measure, if you don't know how to integrate, how will you talk about the 2 now? So how will you talk about L2, LP, right? So all these spaces will come into the picture. You can study these spaces, you can have operators on these spaces. What that does is, it will help you solve differential equations. In most cases, G or most cases it will not be G, we will have G mod H. We will see how the Haar measure can be brought down here. So first of all, if you take this theorem for granted, it just tells you there is a Haar measure on the group. But in most practical applications, we come up with quotient spaces, which, as we saw, are homogeneous spaces, but there is a way, I mean, under some conditions you can push this G to G mod H, right? And if you do that, you can study the L2 space of G mod H. Now for this now if by studying the integral operators on L2 of G mod H, integral operators are very, very well behaved as compared to differential operators. Now by studying integral operators on these L2 of G mod H, you will be able to get the spectrum of the differential operators. The most standard example is coming from modular forms. That is why I am saying this very confidently. And okay, so we will see. So the point I want to make is that this is a very important result, and you should not take this lightly. Okay, so there is an even more interesting result than this, and yeah.
In the definition of locally compact group, you just said that there exists a subset with non-empty interior.
There exists a compact set.
Compact subset means if that set is a subgroup of that group, can we say anything more about the group?
So if you are saying if you have an open compact subgroup, then yeah, you can say something. Then you are assuming something more, right? Then you have a open compact neighborhood of the group around the identity. You are assuming something more. These things are like pro-finite groups and pro-p groups have this property. For example, ZP has this property. I hope you know what ZP is, right? You know. Yes, the inverse limit of Z mod P power n Z. This group has the property that you're talking about. Anyway, but with respect to Haar measure, you can't say anything. But I mean, I don't know if you can say anything more. I have not seen such a result. Okay. Integration over? Yes, you can define, and the measure you are using is the Haar measure.
That's what you have said earlier.
Where is the H coming from now? I don't see where the G mod H is.
Z mod P Z.
No. This is not Z mod P set. This is not Z mod P set. This is an infinite group. This is the periodic integers. Okay, so this is not Z mod P set. Actually, ZP is a very bad notation for Z mod P set because you have these periodic integers, right? Anyway, yes, yeah, I was saying there is another reason why this Haar measure is very important. It's because it's unique. So that is due to von Neumann, but generally it is attributed to Haar. They say but I just wanted to make this historical remark clear. So if G is locally compact, so from now onwards my topological groups are Hausdorff and locally compact. Okay, G is a topological group which is Hausdorff locally compact. Let's say D, L, or let's say mu. Let's not go into D. Let's take mu L is a left Haar measure. We don't know if it is unique yet. So mu L and mu L prime are two left Haar measures on G. Then there exists a lambda. There exists a constant lambda such that mu L of E is equal to lambda times mu L prime of E for every E in your Borel set. Lambda is real. So since mu L and mu L prime are positive real valued function, lambda has to be positive real. Okay, yeah, and one important fact I forgot to mention is that admits a non-zero. Okay, admits a non-zero left and right Haar measure. So the measure of every set going to 0, that is a measure, right? Yeah, you have it. Yeah, that is a measure, and that is the trivial measure. But here is saying there exists a non-trivial measure with all the required properties. Okay, right. So let's call this as theorem 1 and theorem 2. Theorem 2 I will prove. Theorem 1 I will only give you an idea of the proof because the proof is somewhat involved. I don't want to get into the proof because it will not be over by today. I might need some more time. Anyway, so let's start with the idea is very simple. The idea is really beautiful. So idea behind proof of theorem 1. Okay, right. So how do we start? Okay, suppose for the time being that such a measure exists. Okay, so let me fix notation. G is once again a Hausdorff locally compact topological group. Okay, and let's say that a mu L which is a left invariant Haar measure, suppose that it exists, then what can we expect from mu? Okay, so suppose that, so this is the assumption temporarily. So everything in this idea is very heuristic and intuitive. So what I want to do is give you the intuition behind the proof. So there, in some places you might have a lack of rigor. You might be wondering how to actually prove this, or does this always happen? And to show those things is the proof. So yeah, so I'll give you the reference after this. Okay, so suppose G is a locally compact Hausdorff topological group. Mu L is a choice of left invariant Haar measure, and say you have two measurable sets, x and y. Okay, and suppose that you can write x as a subset of some translates of y. Okay. Okay, suppose this happens, finitely many translations you take of y, and suppose this happens, then by the usual properties of measure that we know, we expect mu L of x to be less than or equal to n times mu L of y. How did this happen? First, when you apply mu to the left hand right hand side of this equation, you get mu of x is less than or equal to mu of s1y plus mu of s2y plus etc. But mu is invariant under left translation. So mu of s1y is equal to mu of y, etc., etc., etc. So you get this thing, you get, right? We can rewrite this as mu L x by mu L y less than or equal to. Okay, now this n, so we can ask, what is the least possible choice for n? Or in other words, what is the what is this basically we are asking? Mu L of x by mu L of, okay, even this is not entirely correct, so I will not write it here. So we ask, given an x and y, what is the least number of translates of y you need to cover x? Okay, if x has measure 0, even then you can't say anything. What if y also has measure 0? So this quantity, I mean, so the question that I want to ask, this is again, as I said, most of this is intuitive and this is not rigorous, right? So you must allow for that much. The question that I want to ask is, what is the least number of translates of y we need cover x? Okay, so of course this number may not even exist, right? For example, if your x is the whole space, if x is equal to g and y is just a single point, then you will have to translate it to every other point in g, right? So unless g is finite, this number will not exist in that case. So in general, it is not right for us to expect this number to exist, least number to exist. But for the time being, again in a more intuitive spirit, let us denote this number if it exists. If it exists, we denote this number by this symbol. Okay, this is sometimes called the Haar covering number. Okay, if it exists, we will denote that number by this symbol. Okay, now we make some observations now. The first observation is this x colon y, the Haar number, exists if x is compact and y is open. Why? So, should I give you the answer or should I give you a minute to think about it? It's true. Why? Sorry.
X is complex, so any open cover has a finite collection of subcovers.
So and we are using the fact that translations are homeomorphism. So since y is open, is that clear?
But I'm still thinking, suppose if the topological group has measure 0, then we can't say
The group itself has a measure 0.
yeah.
Then the measure will be trivial measure, right?
And we are taking non-trivial because in the definition
Yes.
we have zero.
Yes. If G itself has measure 0, then every subset of G will also have measure 0.
No, then we can't define Haar measure, no? Because Haar measure is always positive something.
So without defining Haar measure, how can you say that the measure of G is 0?
Lebesgue measure.
So does G always have Lebesgue measure? What do you mean by Lebesgue measure in an abstract topological group? Okay? Or try to rephrase your question.
Why can't we define Lebesgue measure on a topological group?
How do you define length?
Because here also we are taking Borel sigma algebra and
Mhm.
then we are constructing Haar measure.
Hmm.
Similarly, we are defining Lebesgue measure and we are taking the Borel sigma algebra union all those.
Okay, for open balls, you should be able to give a size, right? For open intervals, you are giving length.
Okay, means like how we are defining Lebesgue measure. So Lebesgue measure, first we define Lebesgue sigma algebra. So Lebesgue sigma algebra is basically Borel sigma algebra, and we are taking all those zero.
Yes, so you are completing the Borel sigma algebra.
Yeah. So that is Lebesgue sigma algebra.
Okay.
And there we are defining. Here also somewhat similar we are doing. We are taking.
So there is a very fundamental difference in that. In the case of Lebesgue sigma algebra, and if you want to define the Lebesgue measure, you need to know what is the length of an interval. There is a notion of length. In the topological level, you have a metric. The topology is induced by a metric, and if you have a metric, you have a notion of open balls. Open balls have a given radius, and for those open balls with respect, no, I'm saying in the Lebesgue case, I'm saying in the case of Rn. In the case of Rn, the topology is coming from a metric, and therefore you have a notion of open balls, not open sets. Open balls are much stronger. So if you have an open ball of a given radius r, then you have many ways to arbitrarily define the measure of that open ball. That is how we are doing for intervals, right? What is the measure of an interval? The measure of an interval is defined to be its length, and using that you are defining the outer measure of every other set, right? So that is your starting point. So if you have an open ball, you can, let's say the open ball of radius r has a measure r. I can define like that, and then from there I can start constructing a theory of outer measure, inner measure, etc., etc. But here I don't have open balls. I have only a topology. I don't know whether it is metrizable. I don't know whether it's a metric space. So the construction that you're giving, the way to copy the Lebesgue measure construction is not possible, because in the first step itself we are losing, because we don't have the notion of open balls. You only have open sets.
Can we say Lebesgue measure is Haar measure?
Yes, Lebesgue measure is an example of the Haar measure. So, I mean, last time I told you that whatever measure space you can think of, 8 or 9 out of 10 times that will be a topological group with a Haar measure. Okay, I think we tried to come up with examples today morning. It was not possible. Okay, so this is the first observation. I hope this is clear to all of you. If X is compact and Y is open, then this number exists in the sense this is a number, this is a natural number, you get a number, right? It's not infinity. And the second thing, this number X, Y is translation invariant in X and Y. Because that is how we defined it. What we are doing, we are taking X and then we are covering X by the translates of Y, right? If I had started with some other translate of Y, and then I can bring it back, and then I can do the same covering again, right? For example, if I wanted to cover S, let's write it right. If I wanted to cover T times X, okay, then I will use TS1, TS2, etc. So this number is not getting affected. The translates that I am using, that is changing, but the number is not getting affected. And the same thing goes for Y, right? So this is left translation invariant. I hope that is clear, because we are not considering right translations right now. So translation means left translation. Okay. This is the second observation. What is the third observation? What is the third observation? So this number intuitively
Depends on Y.
Which number? Yes, this is a subset of natural numbers, and I am considering the infimum, least number. So it is unique.
Yeah, if you take more.
Depending on X and Y.
Yeah.
This number is not unique for a given group. Depending on X and Y, this number might change.
No, I am fixing X. So no.
You fix X and Y. If you add more.
Y is also fixed.
Yes.
Yeah, Y is
This number depends on both X and Y. We will change Y soon, but we cannot change Y just like that. We will see. We'll soon get there.
But
So
if you add one more translate of Y in the right side, then the number will change.
no, this is the least number.
Then okay.
This is the least number. That is why it is important. This is the least number. That is why it is unique.
Then it will be unique.
Okay. So this number intuitively it measures how many times what is larger than what? How many times x is larger than y. Again, this is an intuitive point, right? If it takes at least 20 copies of y to cover x, then we expect x to be at least, around 20 times as large as x, as y, right? Sorry?
Not completely. X is less than, right? Less than.
So that is a very nice point, and that is my next observation. This intuition progressively fails if y becomes larger. What does this mean? If you take y to be the whole group, then one translate is enough for me, right? But that does not mean every subset x is as the same size as the whole group. See, that is what my intuition is telling me. If I can cover x with just one translate, then intuitively I expect x to be the same size as y. But that intuition fails if my y is very large. On the other hand, if my y is very small, then the intuition is expected to hold, because if let's draw a picture. Let's say this is my x, okay, and so if y is very large, then the intuition does not hold, that is clear. But let's say this is y, small y, this is y, and this is x, okay. Now this is how my y looks like, and if I cover my x with y, let's say like this, okay, I'm covering the whole space with small circles, okay. The size of, this size, the size where it is falling outside x, these things, the place where it is falling outside x, this will be very small, and so the error between the size of x and the size of n times y will become smaller as my y becomes smaller, right? If y were even smaller, then let's say y is like this, even smaller, right? Then I can do like this, I can cover with this many y's, and so this green portion will not be there at all. So that little bit of error can be deleted, right? So if my y becomes smaller and smaller and smaller, the error between the size of x and n times the size of y, or the size of the cover, becomes smaller and smaller. Okay, is it done? It's not.
Size of the x and n times the size of that y become the same.
Yes, so the error in that estimation becomes smaller and smaller. Okay, so that is what I mean by this. The intuition progressively fails if y becomes larger, and also this intuition this intuition progressively succeeds if y becomes smaller. Okay. So, but we have, so we would ideally require y to go to 0, y to become as small as possible, and then in that limiting process we will expect what we are getting to be some form of a measure of x, of the size of x. But the problem is, as y becomes smaller and smaller and smaller, this quantity might go to infinity. Not might, it will most of the time go to infinity, right? Because I'm using smaller and smaller sets to cover, so I need more and more number of sets. Okay, so I need to control that somehow. So this is where the assumption of local compactness comes into the picture. Okay, so you fix an x star which is an compact set with a non-empty interior. Non-empty interior. Okay, fix this compact set, and then and for every open set V, so U and V are open sets, right? We are on the same page on that. U and V are open sets. So for every open set V, define MV of X, where X is again a compact set. Okay, you define this to be, I'll just write compact. Okay, define this to be x v by x star v. Okay, where v is open. Let us write that also. Okay, now we have hopes to let v go to 0. So if v is becoming smaller and smaller, the numerator will go to infinity, but at the same time the denominator will also go to infinity, because x star is again another compact set with a non-empty interior. So we expect this ratio to approach some limit, and we expect this ratio in the limit to give us some form of measure. So that is our guess, right? So let me repeat.
I didn't get this ratio.
So okay, we need to, okay, we make this observation here that suppose mu is a Haar measure, then 2 times mu is also a Haar measure. Okay, it will satisfy all the properties, it is translation invariant. So if you want to prove something is a Haar measure, or if you want to define a measure on G which you want to be a Haar measure, then you can only hope to define it up to a constant. Okay, because if I take your definition and if I multiply it with some other number, some other positive number, that will again be another Haar measure, right? So whatever you are defining, for the most of the cases you can only expect to define it up to a constant, but that constant will be fixed if you say that this set should have measure 1. Okay, so I have this Borel sigma algebra Okay, I want to choose a set from there and say that this set has measure 1. I'm choosing the Haar measure which is unique up to a constant. I mean, I'm assuming theorem 2, which is unique up to a constant, and I am fixing that constant in such a way that this set which I have chosen should have measure 1. Okay, now so we need to choose that set properly. We know that compact sets have finite measure. That is one of the requirements of being a Haar measure. We know that compact sets have finite measure, and then from our intuition from Lebesgue measure, we expect sets with non-empty interior to also have non-zero measure. Two things we are doing. So we need to choose an x in such a way that 0 less than let's say I should not put mu, so I'll put x star less than infinity. So let me just put this in green color. We don't know whether this exists or not. Okay, but if it exists, this is called normalization. Normalization. We are fixing a constant. We know that it is unique up to a constant, and we are fixing the constant. But again, so one of the easiest ways to do that is to say that a particular set has measure 1. Okay, so we choose a set x star which we expect to have non-zero, non-infinity measure. It should be in between, so that I can invert it. Okay, another way to do this is that whatever Haar measure you give me, I will consider mu of E. So E is any Borel set. I will consider this measure. This is x star. Okay, now if I have an x star which has non-zero and non-infinite measure, so non-zero finite measure, then this is a constant, right? 1 by mu of x star is a constant. So whatever Haar measure you give me, I can divide by that constant, which will again give me another Haar measure. But this, if I call this nu of E,
There is one theorem that any two Lebesgue measure, suppose you have.
What do you mean by any two Lebesgue measures?
Suppose you have defined two Lebesgue measures.
What do you mean by defining two Lebesgue measure?
Lebesgue measure, like you are saying this constant now. They are let's say mu1 is a measure, mu2 is a measure, and they are I think one is Lebesgue measure and one is Borel measure on this real number. Okay, so they are this Lebesgue measure is c times some constant times Borel measure. So
Yes, this is a generalization of that basically. So here, okay, if you denote this measure as nu of E, then nu of x star is equal to 1, right? Because you will have mu of x star by mu of x star, which is equal to 1. So fixing a set which has measure 1 is equivalent to fixing the constant. Okay, I think if you spend some more time, you will be able to get this. So that is precisely what I am doing here. I am choosing an x star which is a compact set, so I expect it to have finite measure, which has non-empty interior, so I expect it to have non-zero measure also. Okay, right? And I am fixing that to have measure 1. So the way I am doing that is I am dividing out by its size, whatever is the expected size I am getting. So one way to see it is m v of x star is identically equal to 1. Okay, so this is equal to 1 independent of v. Okay, so now
Is the open subset of group or only for groups? Open only for only
no, we are considering only groups. We have not gone to G mod H as of yet, but you can translate open sets, right? So even if you have open set sitting inside a subgroup, and then you can translate it to get an open set anywhere else, and it is precisely those translations that we are using here. Even in the defining property of this Haar number, we use translations. Okay, so my guess for my choice for mu, this is where I am officially defining the left measure of x for any compact set x is, wait, I'll just write this and then, okay. This I am defining to be, or this is my guess, okay, this is my guess, limit v going to 0, this mv of, yes, you were saying.
I want to see means I
Sit here, na, you can see better.
means I'm thinking, is there any relationship between this x and x star?
No,
Just two sets.
yeah,
Comparison.
x star is fixed.
We can compensate.
X star is fixed. X star is my base point. Like, if you want to define the Lebesgue measure, as she was saying, you need to know the sizes of intervals. You need to a priori know the sizes of intervals, right? From somewhere I know that size of interval is this. Okay, using that I am defining. So here there are no intervals, there are no open balls here. So I am choosing a compact set which has non-empty interior, and my intuition tells me that this should have a non-zero finite measure. And if something has a non-zero finite measure, I can invert that and I can multiply by that number which we did there, and then get a Lebesgue measure or get some other measure which is 1 on that set, which equals 1 on that set. Okay, that is precisely what I am doing. So I have this thing, right? This thing that I defined. This gives me somewhat of an intuitive notion of the size of x as compared to size of y. Okay, so with this definition I am taking care of two things. One is that my intuition tells me that the size of y should go to 0. I should take y smaller and smaller and smaller if I want to make sense of this intuition, 0.3, right? But if y is going smaller and smaller and smaller, this number will go to infinity. There is all the possibility that this number might go to infinity, and for a compact set which we expect to have finite measure, our guess is going to infinity, which is not possible, which should not happen, right? So somehow I need to control the growth of this guy, and at the same time I need to fix a base element also, something like fix that this is 1 for me. Okay, both things I am doing here in this definition. I am controlling the growth of x colon v by dividing it by, or at least I expect to control the growth. Okay, there is no guarantee that this thing will not go to infinity or will not go to 0, but I expect some form of control to happen. But there is the one thing which is guaranteed is mv of x star is equal to 1. This is guaranteed from my choices. Okay, now I need to make sense of this. I'll zoom in a little bit. I need to make sense of this expression. What do I mean by this? Limit v going to 0. V is not a real number. Okay, v is an open set. So how can I take it to 0? Right. So what I mean by this is that for, let's say, for every epsilon bigger than 0, okay, there exists an open v0. v0 is an open set for me, such that for every open v contained in v0, the absolute value of mv of x minus mu l of x should be less than epsilon. Once again I am repeating, v and v0 are open sets for me. This is what I mean by this symbol, this limit. Okay, now this is to show that this limit exists first of all, and then to show that the limit is countably additive, inner regular, outer regular, all these things will comprise the proof. This is the intuition. That is the meaning. This is the meaning. What I have written here is the meaning of that.
That open set going to 0 means open set, right? Tending to 0 means
This is
the meaning of the definition, right?
this is the meaning. For every epsilon there exists open sets as that. This is what I mean by this limit. Did I make a mistake?
What is
I don't think there is a mistake.
were you use v0 in that?
No, she is thinking like you just find out what is the normal limit definition, right? There exists a just like that. She is asking how this open set tends to 0 like that.
No, this is, see, that is what I said. This is just a symbol. This is just a symbol to get the intuitive understanding that v is becoming smaller. What this symbol means is written here. This is just a symbol. This is not similar to limit x going to 0. This is just a symbol. And what this symbol means, I have written in terms of like epsilon and deltas. Okay, so this is my guess, or this is my candidate, which I expect to be a left Haar measure, and it indeed is a left Haar measure, and it is normalized by the fact that this thing happens. So from here, since this is identically equal to 1, my mu L of x star is also equal to 1. this guy is identically equal to 1, right? So mu L of x star is equal to 1. This is a given for me, right? So the Haar measure, so my candidate for the Haar measure is normalized in such a way that mu L of x star is equal to 1. Okay, and this is where the non-uniqueness comes into the picture. There is a choice of x star involved in your definition of MV or mu L, whatever, and depending on that choice your Haar measure might change. So this is just an existence, I mean not even a proof, this is the idea of an existence proof.
Here V tends to 0.
Hmm.
Okay. So V is fixed one. Na? You have taken V as a open.
V is not tending to 0.
For every epsilon we can find a V naught.
Yes.
Such that for every V contained in that V naught.
Huh.
For every open set V contained in the V naught, that inequality will happens.
Hmm.
For every
Why
open
we are
V.
taking like this?
This actually works with our intuition, right? Okay, I should not put modulus here. This is not a modulus, sorry. Yes. No, this works with our intuition, right? What was the intuition? The intuition was that we need to take smaller and smaller open sets to cover the space X. But so that is precisely what is happening here. We are taking smaller and smaller open sets here. This is just a symbol. Limit V going to 0 is just a symbol. This is not like limit X going to 0. X is not going to 0. V is not moving towards 0. The idea behind this is V is shrinking.
How do you get the UL of x star is equals to 1?
This thing. So for every open set, so for every open set V, this thing is identically equal to 1, right? So whatever thing you put here, so this is always equal to 1. MV of x star is always equal to 1. So if I choose my mu L of x to be equal to 1, then this is always satisfied, right? So whether this is again well defined or not is again another question. So all those questions will be answered in the proof, and for that I will direct you to the proofs. Yeah, so I think this is a good time to give you the reference. The reference is Haar integral. This is the name of the book by Leopold Nachman. This is a very nice book. He gives a lot of intuition and gives the details of proof in, like, he doesn't skip very much, he gives a lot of details of proofs also. Okay, right. So the next thing, how much time do I have left? Okay, I have 15 minutes left. Let's see. Let us try to prove theorem 2. Proof of theorem 2. Okay. What does it say? If you have two Haar measures, then one is a constant multiple of the other, right? So we recall a few more things from functional analysis this time. Okay, we recall a few more things from functional analysis. So first one is the Rees-Markov theorem. Can anyone tell me what is the Rees-Markov theorem? Okay, so if X is a locally compact Hausdorff, all those things, whatever we want. Okay, X is locally compact Hausdorff. then you have cc of x, right? Let I be a linear functional. Okay, I is a positive linear functional. ये अच्छा. Okay, I is a, I'll just write it here. I is a positive linear functional on cc of x. Okay, real valued, complex valued, sorry, it is not real valued, complex valued. I is a positive linear functional on cc of x. What does it mean for, I mean, linear functional, you know, what does it mean for it to be positive? If your f is positive, so this means that f bigger than 0 implies I of f is bigger than 0, bigger than or equal to 0. This is the meaning of positive linear functional. So if you have this, then for every such functional you have, so for every I which is a positive linear functional from cc of x, you have, there exists a radon measure okay, there exists a radon measure nu such that I of f integral over x f d nu. Okay, yes. Okay, this is Rees-Markov theorem, and this is a precursor to Rees representation. This is, or one of the forms of Rees representation theorem. Right, so now what we do is, so there is this dual object to Haar measure, which is the Haar integral. So if you have any measure, the converse of this part is obvious. If you have a radon measure, okay, if you have a radon measure on, let's say, mu, then integral over x f d mu, f goes to this guy for f is in cc of x. This is a positive linear functional that you can show from the properties of the measure mu, simply by that you can show. Okay, but what the Rees-Markov theorem says is that the converse is also true, and this is sort of an identification. So measures can be identified with functionals. So if you put radon measure here, then you will want your functional to be positive. Okay, so this is an identification, and we shall prove the uniqueness using this identification. Yeah, without also you can do, but we shall prove this uniqueness using this. Yeah, and there is to prove that this is an identification, you might have to use Urysohn's lemma. What does Urysohn's lemma say? You can separate compact and open sets.
So mu is always mu
If
I के बीच में वर्णन होगा कि क्योंकि रेडॉन mu हर एक फंक्शनल ओवर दैट सीसी स्पेस ओवर एक्स, सीसी एक्स के ऊपर अगर हम कोई फंक्शनल बना रहे हैं तो
पॉजिटिव फंक्शनल,
हाँ पॉजिटिव फंक्शनल, तो वो फंक्शनल के लिए मेरे को एक रेडॉन मेजर मिल रहा है.
हाँ,
तो आई अगर हम एक लिया तो आई से कॉरस्पॉन्डेंस मुझे न्यू मिला.
या
हाँ, तो आप ये सेकंड लाइन में क्या कह रहे हैं कि
The
रेडॉन
converse construction, हाँ।
रेडॉन मेजर है हमारे पास, तो क्या हम उससे फंक्शनल बना सकते हैं या नहीं?
यस।
तो रेडॉन मेजर म्यू है, तो आप फंक्शनल बना रहे हो वैसे। और वो एफ यूनिक होगा? नहीं।
F is in CC of x. This is I of f. This is my definition of I of f.
कनेक्ट कैसे कर रहे हैं आप?
म्यू है ना, इंटीग्रल इज विद रिस्पेक्ट म्यू।
आई को म्यू के साथ दिखाना था 1-1 कॉरेस्पॉन्डेंस ना?
No, I did not say 1-1 correspondence at all. I said identification.
कन्वर्स ट्रू है, तो इसका मतलब कि अगर मैंने आपको म्यू दिया तो आपके लिए आपको मुझे आई निकाल के देना है।
But I'm not sure it is a one. I mean, it is not obvious that it is a 1-1 correspondence.
हम लोग फंक्शनल में करते हैं, डिस्ट्रीब्यूशन में करते हैं। डिस्ट्रीब्यूशन में हम CC x के जगह CC इंफिनिटी स्पेस ले लेते हैं, और CC इंफिनिटी में हम ये दिखाते हैं कि कोई भी लोकली इंटीग्रेबल जो फंक्शन है उसके कॉरेस्पॉन्डेंट मेरे को एक डिस्ट्रीब्यूशन मिलेगा ही मिलेगा। मतलब कि आप मेरे को कोई भी एक लोकली इंटीग्रेबल फंक्शन दे दो, मैं उस लोकली इंटीग्रेबल फंक्शन के कॉरेस्पॉन्डिंग एक फंक्शनल निकाल दूंगी, और अगर आप मेरे को कोई डिस्ट्रीब्यूशन दे दोगे तो मैं उसके कॉरेस्पॉन्डिंग एक वो लोकली इंटीग्रेबल फंक्शंस निकाल दूंगी। लेकिन ये मेजर वाला केस उसमें नहीं आता है, मेजर डिस्ट्रीब्यूशन अलग होता है।
ठीक है, दिस इज आई एम टेलिंग यू कि मेजर में भी होता है ये, like so. Sorry, if you use Ureson's lemma, what is the Ureson's lemma in the case of locally compact groups? You have so for every k, okay, this is contained in U is open, k is compact, there exists an f in CC infinity, CC of x, not CC infinity, CC of x such that, देखा तुम्हारे साथ आके मेरे दिमाग में CC infinity आया, chi k, this is the characteristic function of k, this is less than or equal to f, less than or equal to chi u, this is the characteristic function of u. So what does this mean? F is equal to 1 on k and f is equal to 0 outside u, and f is continuous with compact support. Okay?
Support of f is in U.
Yes, because it,
We can prove this.
huh?
We can prove this.
Yes, this is known as Ureson's lemma.
I think this without any. This is general true.
Yeah, this is true in general. You don't need topological groups. हाँ, partitions of unity को लेके हम कर सकते हैं. Yes, you can do it. I think that is for metric spaces, but this is true in general. I'm not sure. Anyway, leave that. So using that, you can show that this is an identification, somewhat of an identification. Okay. Now to prove the proof of uniqueness is, how many of you know Fubini's theorem? What does that say? क्या बोलता है Fubini's theorem?
कोई मेजरेबल फंक्शन है, f मेरा मेजरेबल फंक्शन है, प्रोडक्ट स्पेस से r इंफिनिटी भी ले सकते हैं, r यूनियन इंफिनिटी ले सकते हैं। तो अगर मेरा क्या कहते हैं, अगर वो इंटीग्रेबल है, फंक्शन से इंटीग्रेबल है प्रोडक्ट स्पेस से, तो उसको हम उसका जो इंटीग्रल ओवर x क्रॉस y f d न्यू क्रॉस न्यू, मतलब न्यू मेरा x का मेजर है और न्यू मेरा y का मेजर है, तो उसको हम इंटीग्रल x, हम दो चीज डिफाइन करते हैं, f सब x f सब y क्रॉस सेक्शंस लेते हैं, तो उसको हम पहले x के टर्म में
हम्म।
इंटीग्रेट करेंगे, फिर उसके बाद y को हमेशा लेके जाएंगे, उल्टा
So,
भी कर सकते हैं।
basically it says when you can change the order of integration. Okay, good that you know this theorem. So anyway, so we start with, okay, we shall prove for integrals the proof of theorem 2. This is a quick proof. So let nu and mu be two left invariant Haar measures on G, capital G. Okay, you take G in G, CC of X, choose G in CC of X, or no, not X, G. Okay, G is my locally compact space such that integral over G, small g, d mu is equal to 1. D mu or d nu? D mu is equal to 1. Okay, choose such a G. Then what happens? Okay, now you take and you define lambda to be, so lambda is the constant that I will eventually get. Okay, you define this to be integral over G, G of x inverse d nu. Okay, so here I mean you should know, like, it's not G of x, it's G of x inverse d nu. Okay, this is my choice for lambda. Now you let f, this is let f be in CC infinity, CC of G. Okay, f be in CC of G. If I show that integral over f d mu is equal to lambda times integral, so if I just write integral, then it is integral over the whole space. Okay, integral f d mu is equal to lambda times integral f d nu for every f in CCG. Then using whatever I told you before, Rees-Markov and Urayson's lemma, you can show that mu is in fact lambda times nu. Okay, this for every f in G will imply this. So these are basically dual considerations. You must be able to look at these things as measures on the one hand, at the same time as functionals. This is a dual too. It's like we can identify vectors with their finite dimensional vector spaces with their duals, right? V is isomorphic to V star if V is finite dimensional, and the identification comes via basically a finite dimensional version of Rees representation. Every functional can be written as an inner product, basically, if you have finite dimensional real vector spaces, right? So it's the same philosophy here. Okay, so this is what we shall try to prove. So this is what we shall try to prove. So we start on the left with this. So start with integral f d nu. I think the lambda will come here, I'm not sure. Anyway, we'll see. You start with integral f d nu. This is equal to integral G d mu, integral f d nu. Okay, I should be careful of the variables also. Okay, G variable I am writing as y and f variable I am writing as x. G of y d mu of y integral f of x d nu of x. This is okay because I have chosen my G to have integral equal to 1. See G, right? Integral G d mu is equal to 1. So this thing I am just multiplying by 1 basically, right? So this I can write as I can do a change of variable. This is equal to, what is this equal to? What did I do? I think this is right translation. Okay. Integral g of y d mu of y integral f of xy d nu of x. Okay, how did I get this? I am putting w as, or let's say so this y is coming from here. Okay, this y is coming from here, right? So you put w as, what will I get? I need to have x is equal to y inverse of w, so you have yx, yx xy, I don't know. If you do this, then nu of d nu of w will be equal to d nu of yx. Okay, but this is translation invariant, I think. Okay, now I understood. I should do the other way. Don't do this. You define a new variable w as xy. Okay, define this new variable as xy. So inside this integral, y is fixed because it is coming from this y over here. Okay, so again you can think of it as using Fubini's theorem. So for every y, this I can make this substitution, and since the integral is running through the whole of g, this thing will not change the domain of integration, because translating by y will give me g itself. Okay, and if I do this, then what will happen? D, okay, maybe I am making a huge mistake here. I want wy to be equal to x. Okay, yes, so yeah, this is, again I'm sorry, this is not this one. I want wy to be equal to x. Okay, but if I do this, wait, I'm not sure. I think I've made a mistake somewhere. Okay, okay, for the time being, let us assume that this happens. Let's see if we can do something else. Okay, there is I'm not able to justify how I'm getting this, but still let's assume that this happens. Okay, and let's go forward. So if this happens, then again I can take this g of y inside. Again I'm using Fubini's theorem. Okay, I can take this to be equal to integral d mu of y integral f of xy g of y d nu of x. Okay, and then what will happen? I will take yeah, here everything. So I need to have just y over here. Okay, so what will I do? I will take y or let's say z is equal to xy. Okay, then my y will be x inverse z. So, and d mu of y will be equal to d mu of z, because this is left translation invariant. So here my x is constant, y is varying. Okay, and since I am multiplying on the left by something, and since mu is left invariant, I will have this. So this thing will be integral d mu of z. Okay, and you will have integral x y z f of z, g of y is x inverse z, right? X inverse z d nu of x. There is no change there. Now this I can take it here, integral f of z d mu of z. Okay, this is one thing. Again I am using Fubini's theorem, g of, no, here I am not using Fubini's theorem, sorry, d nu. Okay, now again in terms of wait, again I am making a mistake. It should be okay, here I am supposed to get lambda. Okay, but anyway, I think no, so there is a z coming here.
So z should not be there, no?
Yeah, z should not be there. Actually I should have, how did I, yeah, this is how I define my lambda, right? This is how I define my lambda. I want it to be z x inverse, I think. Okay, let's see if x inverse z is equal to y, or I want it to be y inverse, right? Okay, suppose this happens, then yeah, I think it will work. Z inverse x is equal to y. I am just taking inverse on both sides. Okay, इसको देखो, उधर मत देखो, इसको देखो.
X inverse z is equals to y.
No, y inverse. If I am doing this change of variable, then I am getting z inverse x is equal to y. Now here I will have dx is equal to dy, d mu of is equal to d mu of y. Because here I am translating on the left by z inverse. Here the problem was I was translating on the right. Okay, so I don't know if mu is right invariant. I only know that mu is left invariant. Understood? See here, x is my variable and I need it to be, okay, this is mu or nu, same works, it works for nu also. Okay, it works for nu also. Here I have x inverse z is equal to, sorry, here, okay, what is the problem here? I want to get d nu of x here, but if it is x inverse of z, x is my variable and z is the constant, z is which I am translating with, right? But I am translating on the right, the multiplication is on the right, so I don't know if mu is right invariant. I only know that mu is left invariant. Okay, so if I do this, then this thing will be integral g of y inverse, right? Okay, yeah, y inverse d nu y. This was my lambda. So this integral f d nu is lambda times integral f d mu for every f. So that is why this lambda should come here, right? So integral f d nu is lambda times integral f d nu. So this lambda should come here. Okay. So we'll stop here. I took 10 more minutes, but it's okay. We'll stop here.